Welcome to The Explainer. Today, we are cracking the code on a concept that is absolutely crucial for your Class 12, JEE, and even NDA exams. We're going to figure out, with mathematical proof, when a function is going up and when it's coming down. Let's dive right in. You know, every single function tells a story. It has its own journey, its own peaks, its own valleys. Our job today is to learn how to read that story, to understand exactly what it's doing at any given moment, without any guesswork. So, how do we begin? Well, we start with what we can see. At its heart, the idea is incredibly simple. We've all looked at graphs, right? If you trace a graph with your finger from left to right and your finger is moving up, hey, the function's increasing. If your finger is moving down, it's decreasing. It's really that intuitive. So here's our game plan for today. We'll nail down the formal definitions, then we'll unlock the most powerful tool for this job, the derivative, and learn its super simple rules. We'll solve a classic problem, tackle some trickier ones, and then I'll show you a shortcut that will be a total game changer in your exams. All right, let's move on from just using our eyes and get a little more precise. It's time to speak the language of mathematics so we can be absolutely certain about our answers. So what does it really mean for a function to be increasing? Well, formally, it means that as you pick a bigger x value, the function's value, f of x, also gets bigger. Or it can stay the same. Now, that or stays the same part is super important. It's why an increasing function can have little flat spots. And you guessed it. The exact opposite is true for a decreasing function. As you move to the right on the x-axis, the function's value either drops or stays the same. Again, those little horizontal plateaus are totally allowed. Now, let's zoom in on a detail that trips a lot of people up, the difference between strictly increasing and just increasing. Think of strictly as meaning it's always on the move, always rising, no flat spots allowed. The same goes for strictly decreasing. This little distinction is a big deal, especially when we start using our next tool. But let's be real. Drawing a graph for every single function, it's slow, it's not always practical, and sometimes it's just plain impossible. We need a better way. We need a tool that can just tell us which way the function is heading at any point. And here it is, the master tool, our secret weapon, the first derivative, f prime of x. Seriously, think of this thing as your own personal direction detector. It's the key to this whole business. And you know what the best part is? This incredibly powerful tool has a manual that's about as simple as it gets. All you have to do is check one thing, its sign. Is it positive, negative, or zero? That's it. This table right here, this is your cheat sheet for everything. If the derivative is positive in an interval, the function is strictly increasing there. If it's negative, it's strictly decreasing. And if it's zero, the function is flat. It's constant. It's that simple. The sign of the derivative tells you the story. Okay, enough theory. Talk is cheap. Let's get our hands dirty and actually solve our first case. We're going to put this tool to the test right now. And here's the battle plan. This four-step method will work for you every single time. 1. Find the derivative. 2. Find the critical points by setting that derivative to 0. These are the potential turning points. 3. Plot them on a number line. And 4. Check the sign of the derivative in the new intervals you just created. So let's take a classic example. f of x equals x squared minus 4x plus 3. Step 1, find f prime. A little power rule action and boom, we get 2x minus 4. Easy enough. Step 2, find those critical points. Where could this function change direction? We just set our derivative, 2x minus 4 equal to 0. A little bit of simple algebra tells us our only critical point is at x equals 2. This is the only place the story can change. And now for the final step, the moment of truth. We check the signs on either side of 2. Let's pick an easy number to the left, like x equals 1. Plug it into our derivative, f prime, and we get negative 2. Negative sign means our function is decreasing. Now let's try a number to the right, say x equals 3. Plug that in, and we get plus 2. Positive sign means the function is increasing. Done. Case closed. So that was a pretty straightforward polynomial. But the real magic of this method is that it works on the tricky stuff too. Trig functions, logarithms, you name it, the same 4 steps apply. Let's take sine of x. What's its derivative? Cosine of x. So the behavior of sine, when it's rising or falling, depends completely on whether cosine is positive or negative. And we know that. As you can see on this timeline, from 0 to pi over 2, cosine is positive, so sine is increasing. Then, from pi over 2 all the way to 3 pi over 2, cosine is negative, so sine is decreasing. And here's a slide you might want to screenshot for your study notes. These are some of the heavy hitters you'll see on exams all the time. For example, e to the x and natural log of x, they are always increasing, and 1 over x is always decreasing. Knowing these by heart can save you precious seconds. Okay, you've been patient. You've learned the method. Now it's time for the secret I promised. The pro-level move for when you have lots of critical points and you need to be fast and accurate. It's called the wavy curve method, and it is a massive time saver. You still find and mark your critical points on a number line, but then you only have to test one interval, the one on the far right. Once you know its sign, you can usually just alternate the signs as you move left across each point. Now, just a small warning, you have to be a little careful with repeated roots, but for most problems, this is lightning fast. And just to wrap things up, let's learn one final piece of vocab. A function that is always increasing or always decreasing across its entire domain, well, it gets a special name. It's called a monotonic function. Just a nice, clean way to describe a very well-behaved function.
So there you have it. The secret is officially out. The derivative is the key that unlocks the whole story of a function's behavior. You have the master tool now. The only question left is, which function's secrets are you